Good afternoon. I am Natalia Vallejo Montoya, and today I'm going to talk about my contribution to my group project called Digital Data Link. The objective of this project is to be able to design a Bluetooth system so that information can be transmitted wirelessly between the two devices. This is going to be really useful because we won't have to use a cord to do that. The quad chart, as you can see, our system criteria to be able to transmit information, we need a transmitter and a receiver. Both of these systems consist of mixers, oscillators, QPSK modulator and demodulator, low pass filters, high pass filters, band pass filters, power amplifiers, RF amplifier, etc. And now I'm going to talk about the transmitter side that I worked on. I worked on the mixer, and for the mixer I have a mixing stage. It's an up conversion mixer with current mirror topology. This was designed for Bluetooth standards by two Chinese people, and they provided the table with the parameters for the values of the capacitors, of the resistors, and the transistors width and length. The mixer consists of several parts. It has the IF input driver stage, which are the bottom transistors, and they transfer the received incoming signals from voltage to current that serves as the bias current for the transistor at the top part. And these transistors will be the local oscillator switching stage, which modulates the current, and they are connected to the two other transistors at the top, and they are what are called the current bleeding circuit, which is what makes the switches ideal, and they are tuned transistors, and the purpose is to have a high conversion gain and a low noise figure. Then we have the low stage part of the mixer, which consist of the capacitors and inductors at the top, and they act as bandpass filters to reject further products except the RF frequency at around 2.45 GHz, which is the frequency we would like to have. And then we have the other part of the mixer, the output buffers. They are 50 ohms output impedances, and we also have the capacitors. These capacitors are DC blocking capacitors, and they isolate the input or output from the DC source. Then we have the power amplifier for the transmitter, and we are using the BFP650 bipolar transistor, which was designed for applications with frequencies from 2.3 GHz to 2.5 GHz, and we are using it so that the signal that was modulated is boosted with this amplifier, and so that it can be transmitted from the antenna's transmitter to the antenna's receiver. And as you can see in the simulation, the power amplifier produces a gain of 17.27 dB at 2.45 GHz. The last part of the transmitter is a low pass filter, and the purpose of this filter is to remove the harmonics from being transmitted. We decided to use a higher frequency than 2.4 GHz because we want to avoid losing power. Then on the receiver side, as you can see on the block diagram, my contribution is the bandpass filter, the RF amplifier, and then the IF amplifier, as well as the bandpass filter for the IF or intermediate frequency. And we start with the bandpass filter. The purpose of this filter is to prevent unwanted frequencies from entering the receiver, and it allows signals from a selected range to be heard. That's why we chose a bandpass filter with a center frequency of 2.45 GHz, and a bandwidth of 0.2 gigahertz. And it's a Chebyshev design because it provides a faster roll-off speed that enables the cutoff performance to be reduced to a single number. As you can see, that's the simulation part, and we have the center frequency just as we said it was 2.45 gigahertz. Then we have the RF amplifier. This is the next stage of the design because we want to amplify the radio frequency signal from the antenna so that it can be processed and converted into a higher power signal. We designed it with this RF amplifier with a low noise amplifier by Infineon Technologies company, and because it has a 2.3 to 2.4 gigahertz application. And then as you can see in the simulation, the design has a gain of 19.2 dBs and an output power of 29.2 dBm. And the transistor we are using for this design is a BFP640, and amplification starts at 1.5 gigahertz. Salomon's contribution on the local oscillator helps us have a local oscillator of 2.440 gigahertz, and since the message signal has a frequency of 2.45 gigahertz, the intermediate frequency results in 10 megahertz. For this reason, we want to have a bandpass filter that is designed with a center frequency of 10 megahertz so that we can focus on that frequency and filter out the other frequencies that we don't want. And this bandpass filter will guarantee a better performance of the receiver. The simulation just shows and ensures that we have that frequency, the 10 megahertz frequency. And then we also have an intermediate frequency amplifier because it helps us increase the signal. And for this design, we are using a ceramic filter called Murata SFEC10M7GA00, and it provides a 230 kilohertz of a bandwidth in a 40 dB IF amplifier. And we are cascading two transistors, the THS3202, to provide a higher gain, because the higher the gain, the better the sensitivity, and we also have a higher performance, and this results in a simulation of a gain of approximately 40 dB gain at 10 megahertz.